In this lecture video, we're going to look at how to perform two-tailed tests about a population median. So suppose that we want to perform an hypothesis test of the following form. The null hypothesis says that the population median is equal to some specified value, m sub 0, against the alternative that says that the median is not equal to that value. And we want to perform this test at a significance level of alpha, or as we've discussed before, a level approximately alpha or perhaps no greater than alpha. So in words, this is testing whether there is sufficient evidence to conclude that the population median is different than the specified value m sub 0. And so let's continue to consider EXST as our candidate test statistic, and let's look and see how EXST behaves under the null hypothesis, but also under the alternative hypothesis. And so this graphic shows three distributions, one with a median equal to cap m sub 0, which corresponds to the null hypothesis being true. That is this green curve here. So for this potential or possible distribution or population that we're sampling from, in that case, the population median is equal to the specified value m sub 0. And then we have two other potential distributions. One that corresponds to the population median being something less than cap m sub 0. So that's this red curve here to the left. And it's centered at a value m that is less than m0. But we also have another distribution. The other potential way that the null hypothesis could be false is if the population median is actually greater than cap m sub 0. So we have these three possibilities represented. And so we see here that if the null hypothesis is true, and I'm saying here the boundary condition of the null hypothesis, actually there's only one situation considered in this null hypothesis, and that is that cap m is equal to m sub 0. So I'm going to at some point change that statement right there to reflect this. But we see that when the null hypothesis is true, then the probability that a particular observation from this distribution is greater to the right of m sub 0, okay, that probability, which is given by the area under the green curve to the right of m sub 0, we see that that probability is 0.5. On the other hand, let's suppose that cap m is actually less than m sub 0, so that the distribution that we're sampling from is actually over here. Then we see that the probability of getting an observation that is greater than cap m sub 0, which is given by this probability here under the left red curve to the right of point m0, we see that that is something less than 0.5. And finally, if the distribution we're sampling from has a median that's greater than cap m sub 0, so for example this red curve here, then the probability of obtaining an observation from that distribution that is greater than cap m sub 0 is going to be something, that probability is going to be greater than 0.5. And so we see if the null hypothesis is true, then p is equal to 0.5. If the alternative hypothesis is true, then p is not equal to 0.5. Either p is going to be less than 0.5 or greater than 0.5. And furthermore, we can see that the farther the true population median is from the hypothesized value, the further away or the farther away p is from 0.5. It's either going to be much, much smaller or much, much larger as cap m moves away from the hypothesized value of cap m sub 0. And so what is the sampling distribution of EXST under the conditions of the null hypothesis? We know that when that's the case, that EXST has a binomial distribution with p equal to 0.5. And again, here is a representative graph of the sampling distribution of EXST under the conditions of the null hypothesis. And so what values would we expect to see EXST take on if the null hypothesis is true? All right, and so we can see from this graph that if the null hypothesis is true, and therefore that this is the sampling distribution of EXST, that there's a very high probability of observing a value of EXST between 2 and 8. And that probability is given by the sum of the areas of the rectangles over the integers from 2 to 8, and that turns out to be 0.979. There's only a 0.021 probability that EXST would take on a value either 0 or 1 or 9 or 10. And so if the null hypothesis is true, then it would be unlikely, it would be unexpected for EXST to take on values 0, 1, 9, or 10. And so we see then if the null hypothesis is true, then the random variable x tote is going to tend to take on values close to the mean of its sampling distribution under the conditions of the null hypothesis, n over 2. If the alternative is true, then x tote will tend to take on values that are either a lot smaller than n over 2 or a lot greater than n over 2. And so what we're looking for as evidence against the null hypothesis are values of x tote that are either really small or really large. In other words, values of x tote that are far away from n over 2, the mean of its sampling distribution, if the null hypothesis is true. Such values are going to provide evidence against the null hypothesis and in favor of the alternative hypothesis. Okay, so to calculate the p-value, we will again make use of the fact that if the null hypothesis is true, in other words, if the median of the distribution is equal to the specified value, cap m sub 0, then x tote has a binomial distribution with n equal to the sample size and p equal to 0.5, which again was represented by that binomial PMF, in this case for n equal to 10 on that previous slide. Now, in order to calculate the p-value for the test, it's a little more complicated in this two-tailed test. And so there are 3 cases that we have to consider, and we're going to start considering those on the next slide. Now, case 1, if the observed value of x tote is equal to the mean of its sampling distribution under the conditions of the null hypothesis, in other words, n over 2, then the p-value is equal to 1. Now, if the observed value of the test statistic x tote is strictly less than n over 2, then the p-value for the test is given by the following formula. It's going to be equal to the probability that the random variable x tote is less than or equal to the observed value of x tote under the conditions of the null hypothesis, plus the probability that the random variable x tote is greater than or equal to n minus the observed value of x tote, again computed under the conditions of the null hypothesis. So there are 2 probabilities that we have to calculate here and add up. This is similar to, if you think back to, say, a 2-sided z-test or a 2-sided t-test about a population mean, the p-value formula takes into account the fact that we have to calculate probability in both tails of the sampling distribution. And so this is reflected in this formula. Now, case 3, if the observed value of the test statistic x tote is greater than n over 2, then the p-value for the test is given by the following formula. It's equal to the probability that the random variable x tote is greater than or equal to the observed value of x tote, computed under the conditions of the null hypothesis, plus the probability the random variable x tote is less than or equal to n minus the observed value of x tote, again computed under the conditions of the null hypothesis. So these are very similar formulas. They depend on whether x tote is less than the mean of the sampling distribution of x tote or greater than the mean of the sampling distribution of x tote under the conditions of the null hypothesis. So there's a little more work to do here. We have to be a little more careful. You know, there are these cases to consider, all right, but it's still not that difficult. Now, we can simplify those formulas a little bit, make our job a little bit easier, by recalling that for every natural number n, given number of trials, the binomial distribution with n trials and success probability equal to 0.5 is symmetric about its mean, which is n over 2. So if we're dealing with the binomial distribution with p equal to 0.5 or 1/2, then the mean of its sampling distribution is n over 2. And we have discussed previously the fact, and shown in various examples up to this point, that this distribution is perfectly symmetric about its mean. And so the implication of that is that the probability that the random variable x tote is less than or equal to little x tote under the conditions of the null hypothesis, which would imply then that p is equal to 0.5, that implies that this probability is equal to the probability that x tote is greater than or equal to n minus the observed value of x tote. In addition to that, the probability that the random variable x tote is greater than or equal to little x tote is equal to the probability that the random variable x tote is less than or equal to n minus little x tote. All right, and so that allows us to simplify the last 2 formulas on the previous slide. And so for the second and third p-value formulas on that slide, the formulas simplify to the following. So if the observed value of x tote is to the left of n over 2, then the p-value for the test is given by 2 times the probability that the random variable x tote is less than or equal to little x tote. Again, computed under the conditions of the null hypothesis. If the observed value of x tote is greater than n over 2, then the p-value for the test is given by 2 times the probability that the random variable x tote is less than or equal to n minus the observed value of x tote. Now, both of these formulas can be easily expressed in terms of the binomial CDF. And so let's take a look at that. So if the observed value of x tote is less than n over 2, then the p-value can be computed as 2 times the value of the CDF of the binomial evaluated at little x tote, again where p is equal to 0.5. And if x tote, the observed value of x tote, is greater than n over 2, then the p-value is 2 times the value of the binomial CDF evaluated at n minus little x tote, again with p equal to 0.5. So we've gone from these somewhat complicated formulas using symmetry of the binomial distribution when p is equal to 0.5, which implies these equalities, gone to these expressions for the p-values, and I've expressed them this way because each of these probabilities is equivalent to an expression involving the CDF of the binomial distribution. Whenever you've got the random variable, the probability of the random variable less than or equal to some value, as I've got here and then here, this is just equal to the CDF evaluated at that value, and in the second formula, the CDF evaluated at that value. So for example, if we had a sample of size 10 and the number of y values greater than the hypothesized value was 2, then the p-value would be given by this formula. And in terms of the CDF, it would be twice the value of the CDF evaluated at 2 when p is equal to 0.5. And you can see that both of these are equal to, we get the same value, 0.109375. On the other hand, if the observed value of x tote was 8, right, so 8 is greater than, let's see, 10 over 2, which is 5. Okay, so then we would use this version of the p-value formula to calculate the p-value. All right, and that again would be 0.109375. If we were to calculate it using the formula specified in terms of the CDF, then it would be 2 times the CDF evaluated at 10 minus 8, where n is equal to 10, p is equal to 0.5, 2 times the CDF evaluated at 2, which again is 0.109375. So we see that we can calculate the p-value for the test using either the CDF or in terms of calculating sums, the individual terms of the sum, and then adding those up. All right, so let's look at an example. So the data in the table below are a random sample from a normal distribution with unknown mean and unknown variance. Again, let me issue the disclaimer that nothing that we're doing depends on the normality of the distribution that we're sampling from. Okay, so we will again frame the question in terms of the population median and use the two-tailed testing procedure just described to answer the question of interest. So the question is there sufficient evidence at the 0.05 level of significance, or something close to that, or perhaps the closest attainable significance level no greater than 0.05? Is there sufficient evidence to conclude that the median of the distribution is different than 0? So here, the hypothesized value of the population median is 0. And if we look at the data, the y values, we see that we've got some positive values. We see we also have some negative values. And so the question is there sufficient evidence in the data to lead us to the conclusion that the median is actually not equal to 0? Okay, so here is the setup of the hypotheses. We're trying to show that the median is not equal to 0. Since that's what we're trying to show, we put that in the alternative hypothesis. The opposite of that goes in the null hypothesis. So the null hypothesis for this test is that the median of the population is equal to 0. We'll assume that, and then let the data try to convince us otherwise. You know, the alternative being that the median is not equal to 0. Now, if the null hypothesis is true, then x tote has a binomial distribution with n equal to 16 and p is equal to 0.5. The next slide shows information about this sampling distribution. And so again, I'm constructing the sampling distribution of X-tote under the conditions of the null hypothesis on my TI-84 calculator. List L1 has the values in the sample space, integers from 0 to 16. The values in list 2 are the values of the CDF, and the values in list 3 are 1 minus the values of the CDF. We need to keep in mind that we're wanting to perform the test using a significance level of around 5%. And if we require that the significance level that we actually use be no more than 5%, then that's going to be even a little bit more restrictive. And so remember that if the null hypothesis is true, if the median of this distribution is equal to 0, then X-tote will tend to be close to around 8, n over 2, 16 over 2, which is 8. If the null hypothesis is not true, then X-tote will tend to be either really small, so down here, or really large up here. Okay, so if we look in list 2, so list 2 gives us the values of the CDF, we see that the probability that X-tote is less than or equal to, let's say, 4 is 0.0384. If we then look in list 3, we see 0.0384 again, and that corresponds to the row for 11, the value 11 in the sample space. But remember, now this is not the probability that X is greater than or equal to 11, because this is 1 minus the CDF. For example, the value 0.9616 here, this is the probability that X-tote is less than or equal to 11. 1 minus that, which is 0.0384, this is the probability that X-tote is greater, strictly greater than 11. So this 0.0384 corresponds to the probability that X-tote is greater than or equal to 12. So we just need to make sure that we understand what the values in list 3 correspond to. The point I'm trying to make here, if we were to use 4 as the lower critical point and 12 as the upper critical point, then the significance level of the test would be 0.0384 plus 0.0384, which is 0.0768. So that significance level is larger than 0.05, and so that's a little bit bigger than we want. So we're not going to use 4 and 12 as the lower and upper critical points. Let's check and see if we use 3 and 13. So let's look at in this list 2 again. We see that the probability that X-tote is less than or equal to 3 is 0.0106. And we see the point in list 3 down here below, we see the 0.0106, all right, in the row corresponding to 12. But again, this is the probability that X-tote is strictly greater than 12. And so this corresponds to the probability that X is greater than or equal to 13. So if instead of 4 and 12 being used as the critical points, if we use 3 and 13, then we're going to come up with a significance level of 0.0212. So that is less than or equal to 0.05, and that is the closest attainable significance level that we can actually obtain, that is no more than 0.05 for this particular situation. And again, this is because of the discreteness of the sampling distribution. And so those are the critical points that we're going to use. Okay, so again, the null hypothesis, the population median is equal to 0 against the alternative that the population median is not equal to 0. Specifying the rejection criteria in terms of critical points, we're going to reject the null hypothesis if X-tote is less than or equal to 3, or if it's greater than or equal to 13. Now we can also calculate the p-value of the test, and if we do that, then we will reject the null hypothesis if the p-value is less than or equal to 0.05, which in this case, because of the discreteness of the sampling distribution of X-tote, this is equivalent to rejecting the null hypothesis if the p-value is less than or equal to 0.0213. For example, if we reject the null hypothesis eventually, instead of saying that we used a 0.05 level of significance, we should say that we used actually a 0.0213 level of significance. Okay, so it turns out in this data that X-tote is equal to 13. If we go back to the original data, if we count the number of observations that are greater than 0, we'll find that we have 13 of them. let's go ahead and calculate the p-value of the test. Let's see here. Note that the observed value of x tot is 13. If x tot is greater than n over 2, then the formula for the p-value is given here. And so if we express this then in terms of the CDF, it's going to be 2 times the CDF evaluated at n minus the observed value of x tot. And so now let's go back to our formula here. And, okay, so the way I've expressed this, actually, let me go back a little bit further. Okay, before we did the simplification, okay, here I'm actually using this formula right here. So you can use any of these, all right, as long as you do the calculation correctly, and you'll get the right answer. Okay, so we get a p-value of 0.0213. Now notice here that in the right panel, I'm calculating the p-value in terms of, or using the CDF, right, which is, again, pardon my going back and forth, all right, but just trying to show how we do these things. Okay, so in that right panel, I'm using this p-value, or formula for the p-value. So they're all equivalent, right? But I'm taking advantage of the capability of the calculator to calculate this probability very easily. So 0.02127, or to 4 decimal places, 0.0213. Okay, so stating our conclusions, if we were using the test statistic and p-value method, then we would say since x tot is greater than or equal to 13, right? Or we could specify this in terms of the p-value, since the p-value is less than or equal to 0.05, but actually, you know, what I would do is I would say since the p-value is less than or equal to what do we say here, 0.0213, okay, there is sufficient evidence at that level of significance to reject the null hypothesis and conclude that the median of the distribution is different than 0. Now, note that based on the p-value of 0.0213, we see that we would reject the null hypothesis for a level of significance as small as 0.0213, which is just another way of restating what I was saying up here before. Okay, so that is the end of this example. In the next set of lecture videos, we're going to be looking at large sample approximations to the sampling distribution of x tot.